Hello everyone and welcome back to On the Spot STEM. Today we will be covering 2019 February Gold number 2. With Yusuko coming up next week, we decided that we should probably post a problem to help you guys prepare. So this problem reads, this is actually called Dishwashing and it's from the Gold contest from last year. And so the problem reads, Bessie and Elsie are helping Farmer John wash the dishes, a more complicated process than one might think due to their lack of opposable thumbs. The two cows decide that Bessie will apply soap and Elsie will rinse. Bessie is given a dirty stack of plates labeled 1 through n, where n is bounded by 10 to the 5th. Elsie has an empty stack where clean plates will go. There's a counter in between Bessie and Elsie for soapy stacks. At each step, either Bessie takes a plate from the top of the dirty stack, applies soap, and then places it on the counter. When placing a soapy plate on the counter, Bessie must either 1. Place the plate on top of an existing non-empty soapy stack, or 2. Create a new soapy stack to the right of all existing soapy stacks. Or, Elsie takes a plate from the top of the leftmost soapy stack. Elsie rinses the plate, then places it on top of the clean stack. The goal is for the clean stack to have all plates in order with the smallest label on the bottom and the largest label on the top. It may not be possible for the cows to achieve this goal for the entire stack of plates, so please determine the length of the largest prefix of the input ordering for which the goal is achievable. And so we have our sample case here, and so let's try to work this out. So the answer to the sample case is 4, and so let's just try to see why. So I guess the most naive way to approach this problem is to consider all prefixes of the string. There are only n prefixes, and since this problem is it tells us the implementation in the problem wording, so all we have to do is convert this implementation to code and get our answer from that. So let's just see how we would approach this input. If there was only one plate, then she would put 4, Bessie would put 4, Elsie would take it, and we're done. Because 4 is the only thing on the stack. Now, if there was 4 and 5, Bessie would take 4, Elsie could take 4 right away, and then Bessie could put 5, and then Elsie could take 5, because then 4 would be below 5 in the final ordering. If there was 4, 5, 2, then consider when we can take the 4. Elsie cannot take the 4 after Bessie puts it down, because if she takes the 4, then 4 will be on the bottom of the stack, and we need 2 to be on the bottom of the stack. Essentially, the lowest number that appears on the prefix of the input will be the first to be taken from Elsie. And the second lowest will be the second to be taken from her, the third lowest will be the third taken from her, and so on. So let's try to simulate this. First, Bessie will put 4 on a new left stack. Now, she can either put the 5 on top of the 4 or on another stack and create a new stack. And let's consider what would happen if she put the 5 on the 4. Well, if she put the 5 on the 4, then when Elsie would be taking the plates, since she has to take plates from the top of a stack before going to the bottom, she's going to have to take the 5 before the 4, and in the result, the 5 will be put inside the stack before the 4. And that's a contradiction, because we need 4 to be put before 5. So that means, if you have a number that's greater than the lowest number in the stack, you should probably create a new stack, otherwise you would yield a contradiction. So we create a new stack with 5. Now, we have to put 2. And where can 2 go? Well, 2 cannot go on the stack with 5 because leftmost stacks have to be taken first. And so if 2 went on the stack with 5, then that would be a contradiction because then 4 would be going before 2. So we have to put 2 on top of the 4. And once we have this, Elsie can take this 2. She takes the 2 first, so that gets crossed out. She then takes the 4, that gets crossed out, and then she takes the 5. So that gets crossed out. And it's from bottom to up correctly. So let's try to simulate it for 4 numbers. And so we have 4. And as I said before, 5 has to be on another stack because it can't be with the 4. 2 can go on top of the 4. And since 2 is the lowest number over here, that means we don't want to do anything else before taking the 2 out. Because if we can take the 2 out right away, then it's a good choice to take it out, because then we can get it at the bottom of the stack and that'll be covered for. So you take the 2 out, and you put it at the bottom of the stack, and then now where would the 3 go? Well, again, if the 3 went on the rightmost stack, then all the leftmost stacks have to be processed first, and so that'll be a contradiction, since then 4 would be processed before 3, which is not possible. So she has to put 3 on the leftmost stack on top of the 4. And then Elsie will take the 3, Elsie will take the 4, and then Elsie will take the 5. And we have a correct order. Let's see what goes wrong when we have 5 plates. So she puts the 4. And now, instead of 2 being the first to be taken, it has to be 1, since 1 is the smallest number here. And then 2 has to be taken, and then 3, and then 4, and then 5. So Bessie puts 4, Elsie has to put it on her new stack, 5. 2 has to go over here, as described earlier. Now, where does 3 have to go? Well, 3 either has to go here or it can go here. And so if it goes over here, then we would satisfy the fact that 3 is less than the base of the stack, but we don't satisfy the fact that 3 is the smallest number up here. Because if you have a given stack, the numbers have to be in ascending order. Since when Elsie takes a plate, she has to take it from the top of a stack. So that has to be the smallest number in the given stack, because otherwise she would have to take a bigger number before a smaller number, which is a contradiction. So we can't put 3 anywhere over here. Now if we try to put 3 over here, as seen earlier, it's a contradiction, because 3 would have to come after the 4 and after the 2, which is not possible. So that's why when placing 5 plates, you cannot have a resolution. So now that we laid some rules for how we want to process these, let's try to describe them more in detail. Essentially, we can call our stacks S1, S2, and Sn, and we'll call this Sk, and we can let each of these be kind of like lists, okay? And whenever Bessie places a new plate, she has to put it in one of these stacks such that the number that she places is the lowest number, that the number that she adds to the list is the lowest number in that list. Because if she added a greater number, then Elsie would have to process greater numbers before lesser numbers, which is not possible. And furthermore, she has to place it so that the number that she places is also greater than all the numbers in lists appearing before it, because leftmost lists have to be processed before rightmost lists. So essentially, if we had, let's say we had something like, I'll just give another case. So let's say n equals 8, and the numbers were like 7, 6, 3, 4, 5, 1, 2, and 8. Okay, so if we try to simulate this with the rules that we just made up, first you'd have to put the 7. So first of all, we can just try to see if we can simulate all 8 of these, right? So if she tries to simulate all 8, then she puts the 7. Then the 6 has to go here, since it can't go in a rightmost stack. The 3 has to go on top of the 6. And when she tries to place the 4, it's a contradiction, because she can't put the 4 on top of the 3, because then it won't be the smallest number of the stack. She can't make a new stack with 4, because it would be too small. It would be smaller than 7, which is a contradiction. So instead of simulating 8, let's try to simulate at the midpoint, 4. And we just saw that, so let's try to simulate 4. So she puts the 7, she puts the 6, she puts the 3. 3 is the smallest of these, so that means Elsie can take the 3 right away. And then she puts the 4. And 4 is then the second smallest, and she's already taken 3, so she can take the 4, then she takes the 6, then she takes the 7. So 4 is possible. Our first 4 is possible. So now that we've been given that the first 4 work, our answer has to lie between either the first 4 working, the first 5 working, the first 6 working, the first 7 working, or the first 8 working. And why is this? Well, it's because if you have that n plates work, then obviously n minus 1 plates would work, right? Because when you're placing a new plate, you can it's the same thing as essentially like not worrying about it if it works. So if we know that the first k plates work, we also know that all numbers before it will also work. So our answer either will lie between 4 and 8. So now let's take the midpoint of this range, which is 6. So let's try to simulate the first 6. So she puts a 7, and Elsie has to take 1 out first since that's the smallest one. But Bessie puts 7, she puts 6, she puts 3, and then she can't put 4 because that would be over 3, which is a contradiction. So since 6 doesn't work, we know the answer has to lie between 4 and 6 minus 1, since we already know that 6 doesn't work. So 6 minus 1 is 5. So our answer has to lie between 4 and 5. So let's try to simulate 5 this time. And so she puts the 7, then she puts the 6, then she puts the 3, and then since 3 is the smallest in the first 5, Elsie can take that out. Bessie puts the 4. 4 is the second smallest, 3 has already been taken out, she can put the 4. Then she puts the 5. 5 is the third smallest, 4 has been taken out, so Elsie can take the 5, then 6, then 7, and satisfy. So since 5 works, our answer lies between in the range of 5 to 5, and thus it's 5 for this simple input. So now that we've worked through 2 inputs, let's try to develop an algorithm to solve our problem. We know our algorithm cannot be O of n squared because that'll be too large for n to the n squared, since n is 10 to the 5th. So what we saw earlier that I was trying to do is basically, we know that if k plates work, then k minus 1 work. So if k plates work, then the answer has to lie between k and our upper bound, right? And then what we can do is we can search the middle of this. And then if middle works, then we'll search between middle and upper bound. If it doesn't, we'll search between k and middle minus 1. And so what we're doing at each step is we're taking the midpoint of our lower bound and our upper bound. If the midpoint works, then we can take the midpoint as our new lower bound because we know everything before that will work and we still have the upper bound. Or else, if it doesn't work, we'll have to take low as the lower bound and we'll take our midpoint as the upper bound, or midpoint minus 1, since we know the midpoint doesn't work. So I think many of you are familiar with this type of technique, but it's basically binary search, right? Since we're separating the interval into half at each step, and we can eliminate half at each step. So this is an O of log n time. Just the process of binary searching is O of log n, but we have to multiply by the time complexity it takes to verify whether the first k work. So we still have this O of what, and we have to figure out what that what is. So as I was explaining earlier with how we were doing this, basically when you add a plate, it has to be in a stack such that it's the smallest in that member of the stack, and it's also greater than all plates in stacks that are left towards it, right? So essentially we can represent these stacks as array lists, because adding to an array list is an O of 1 operation. And then also, if we encounter the lowest number when we're trying to do this, and we can keep an array of the lowest numbers and sort them, if we encounter that lowest number, we'll take it out from the array list. And we know that we can only take numbers out from the top of a stack. So when we take numbers out from the top of a stack, that's just removing the last element from an array list, which is an O of 1 operation. So our adding and removing are essentially O of 1, but we have to figure out which stack it goes into. And so the nice property of what we have is that it looks essentially like this. So these are the lower numbers, and these get higher as you go on, and the numbers towards the right are generally higher towards than the numbers towards the left. And so since we have like a monotonous sequence with what our stacks look like, we can binary search for what stack a plate will go in. And this is O of basically log stacks for each number that we put in, and stacks can be up till n. So this is times O of log n. And then we have to do this k times if we're testing a prefix of length k, and k can be anywhere from 1 to n, so we're going to call this O of n. And this yields an O of n log squared n algorithm. And this is fast enough to pass. And so this is going to be multiplied by a constant factor that's probably like a smallish constant factor, since k will not always be near n, and our stacks will not always be close to n. Okay, so now I'm gonna go over my algorithm for this problem. So just as a recap, basically what we did is that for each we're gonna binary search for the correct answer to the problem, and for each prefix we're gonna simulate the problem as it is, and then we're just gonna test whether it works or whether it doesn't, and we use that to drive our binary search. And when we're adding something or removing something from the stack, we can use array lists, and we binary search to see what stack that is, and that yields an O of n log squared n algorithm. So over here, all I have is values, which is essentially the array that we're storing the values in for the problem. So for the sample case, it would be just those 5 numbers. And then we have our integer n, which gets scanned first. This is just scanner stuff. This is print writer. And so this is initializing the values. And then we binary search over here. So this binary search is pretty simple. I'll just explain it a bit though. So essentially, I'll explain my satisfies method later, but we take the middle of our interval. This is our lower bound and this is our upper bound. And if it doesn't satisfy it, but if it satisfies the middle minus 1, then we can return that because we know that that will be the biggest value or the largest value that works. And that's our largest prefix. Else, we'll just return binary search from low to mid minus 1, which is our new lower bound and upper bound. And if it does satisfy for the middle, but it doesn't satisfy for the middle plus 1, then we can simply return the middle because we know that it's going to work for middle, but not middle plus 1, so middle is the largest prefix that works. And otherwise, if it works for middle plus 1, then we establish a new lower bound, which is middle plus 1, and we have our old upper bound, which is high. So now I had a satisfies method in my binary search, so I'll explain how that works a bit. And essentially, our middle value is the middle value we take in from here. And so we create a new array, which is the length of the prefix, and then we take the first the number of values that are in the prefix, and we just set that equal in the array. And so then we have a compare array, which essentially is the first k numbers or the first middle numbers that's sorted. And so if we sort them, then it'll be easier to figure out which ones we still have to remove and which one we've already removed. And then I have a simulate method over here, and it returns an integer. And so if the integer is equal, and this integer that's returned is the number of dishes that have been that are able to be taken by Elsie such that it still preserves the natural ordering. And so the lowest at the bottom and the highest at the top. And essentially, if this number is equal to the number of things that we're scanning in, that means we can say that this prefix works and we will return true, or else we'll return false. So in the simulate method, we take in our middle value, which is the prefix length. We take in our array, and we take in the sorted array, which is this, essentially. And so this is basically this essentially stores all our stacks. So I called it piles, and this is just initializing piles. And so we have 4 variables over here. We have our last pile, we have a counter, we have our current pile, or the beginning pile, sorry, and we have the number of dishes that we still have inside our pile. And so counter is just it's basically the number. It basically keeps track of the smallest element which we have not taken, which Elsie has not taken out yet. And I'll explain more about that soon. So we simulate adding each element of the prefix, so from I equals 0 to mid. And essentially, this is what we do in add. So this is our thing that we will need to add into our piles. And essentially where we place it will be the beginning pile. And then if there are more than 0 dishes in the piles, if there are more than 0 dishes in our piles such that Bessie has put dishes and Elsie has not taken them yet, then we'll binary search for which pile this has to go into. We'll binary search for which pile the plate that we just put in should go in such that it's optimal. And so essentially what this line of code over here does is that in our binary search, if this value is greater than all the previous ones, then as I said earlier, we'll have to create a new pile for it. So I'm just updating our last pile. And so we add this value into where we get this from the binary search, and then we add 1 to the number of dishes since that's in the pile currently. And so this is our removal thing. And so our counter is essentially sorted counter stores the least element that has not been removed yet, and it's what we need to remove. So this is what we need to remove. And essentially, if the piles, since we have to remove from the top of the first pile, that would be our current beginning pile. If the size of that is greater than 0, so that means it has elements in it, and we need to, and the top of this pile, which is pile's cur beginning pile dot get its size minus 1, if that's equal to what we need to remove, then we'll just remove that over here. We'll increment this down by 1 since LC is taking that and that's not in the pile anymore. And we'll plus plus to the counter because now that's been removed. So LC has taken that and now counter plus plus is the next thing that has to be taken from, or next thing that still hasn't been processed yet. And so if this is not true, then we'll just break out of our while loop because that means we cannot do anything further to remove items for now. And if our counter is equal to the middle, and middle is just the length of the prefix. So essentially, if counter equals middle, that means that we've processed all the elements from the all the elements in our prefix. So that means we can just return this because that's the number of elements we've processed. And so while so once we remove these things, the number of piles might change because we might remove like multiple piles at once since if they're sorted well. So while our size is equal to 0 for our beginning pile, we'll just increment this. And what this does, it just brings this variable to the next non-zero pile length. And so over here, I had a binary search to find the pile that our next thing to place should go into. So I'll just explain how that binary search works a bit. So it takes in our lower bound for the pile, it takes in our higher bound for the position of the pile. This is what we want to add, and this is just our pile's array list. So if this is less than the smallest value, or this is less than the value in the left, if this is less than the base of the leftmost pile, then we want to put it in the leftmost pile since we can't put it anywhere else. If it's greater than the rightmost pile, then we'll have to put it into a new pile because we can't put it in the rightmost pile. And then we take a middle over here because binary search. And essentially what this does is that it checks whether it's greater than, whether our middle pile base is greater than or less than what we want to add. And if it's greater than or less than, then we'll do some accommodations that satisfy that. And this is very similar to finding the ceiling of a value in an array, except we're just using like array lists and we're just using the first element in these array lists. Because when we put something in, we want to make it so that it's smaller than the base of the pile which it goes into. And we want to make sure that it's in that spot such that it's the smallest value, such that the base of that pile is the smallest value which is greater than it, which is essentially the ceiling of a value in an array, or the ceiling of a value in our array list. And so that's pretty much all for the problem. So to recap, what we did is that we binary searched. So we saw that if k plates satisfied, or if our length k prefix satisfied the problem, then a length prefix of k minus 1 would also satisfy. So if we found out that k would work, then we could just make k our new lower bound because we know everything before it works and that it's optimal. And then for upper bounds, we start out our upper bound at n, and then at each step we can either decrease that or increase that, or we can only decrease it and we can only increase our lower bound. And so at each step we're dividing the interval into half and we're eliminating essentially 1/2 of the interval. And at each step of this, we check if it satisfies or not satisfies to eliminate it. And in our satisfies method, what we do is we simulate it. And so it's the simulation, it looks a bit complicated, but it's really simple. You just have to follow what the problem statement says. And so what we do is we add each plate from the prefix into the piles. And if it's the lowest plate that still has to be taken out, we'll take that out. And we'll do that while you can still take out plates. And at the end of the day, after all the plates have been put in the piles, if there are essentially no piles, or if there are no plates left in the pile, or we've processed all the numbers in the pile, then we'll say that this length mid prefix satisfies it, and otherwise it won't satisfy it, and that drives our binary search. So that's pretty much all. So now I guess I can submit the problem. So I'll show you how that works. So again, this is O of n log squared n, but it still works. So yeah, that's all. Thank you for watching. If you enjoyed this video, please consider subscribing to us. We'll try to upload more musical videos since contest season is approaching. And if you really like this video, then please consider spreading this to your friends and family so that they can also know about this. Thank you.